last time we had talked about calculating electric fields due to distributed charges. And we had a general procedure for doing this, which involved breaking up the distribution into small pieces, calling the charge of each piece delta Q. Okay, so you divide it up into your delta Qs, and then you draw a delta E due to one piece, just to see how it behaves and get a sense of how things are going to be put together. You write an expression for delta E. So let's write it this way. Write an expression for delta E of one piece. Step 3, you just add them up. So we're taking the sum up all the delta E's, essentially applying the superposition principle. And then the last step is check the result. So last time we talked about the example of a uniformly charged rod. So we had a thin, for instance, a thin insulator, maybe a glass rod or a plastic rod that you rub in with silk or something like that, and you apply a uniform charge over the surface. And we had looked at finding the electric field due to this charge distribution at a couple different points. We did one case where we had some observation location at some random place, okay? And we talked about how you could do this numerically, okay? And what you actually be doing in lab next week, you'll actually be doing that as a computer modeling exercise, where you just break it up into pieces, treat each piece as if it were a point charge, find the delta E due to each piece, and add up all the delta E's. Okay, so you can do that numerically. You can do that computationally. You can do it by hand if you want to, but it would take a long time depending on how many pieces you had. So a computer is very useful for doing a general calculation like that. In certain situations, we might want an actual symbolic expression, an analytic solution to this situation, to this problem. And the advantage is you have a symbolic expression that will work anytime you see a situation like this. The disadvantage is sometimes you can't actually get a function or integrate a function that will give you a symbolic answer. But for this case, at a particular special location, namely any points along this perpendicular bisector, we were able to come up with a symbolic expression for this result. And we found that the magnitude of the electric field of a uniformly charged rod was equal to 1 over 4 pi epsilon 0 Q over R times the square root of R squared plus L over 2 squared. Okay, so R here is the distance, I should say the perpendicular distance from the center of the rod. So it's a distance away along this perpendicular bisector. Okay. Q is the total charge. L is the length of the rod. Okay. So that's a general result. If we see a situation like this, we want to find the electric field along that perpendicular bisector, we can just plug in and get the result. Knowing that, and this only gives us the magnitude of the field, so we know that if this were a positive charge, it's going to be pointing away from the center. If it were negatively charged, it would be pointing in the opposite direction, right? So we can infer the direction just from the sign of the charge. Okay. Now, that we didn't do last time was the last part, which was check the result. So how can we check this result? How can we see if this result actually makes sense? If we did our analytic integration and actually got a expression that is correct, what do we want to do? Well, okay, if you're saying, imagine getting rid of this charge rod and placing a point charge at the same place and see if you get the same electric field. Well, would you get the same electric field? And this is kind of the critical issue. If I had, let's say, this is a charge of, I don't know, say 10 nanocoulombs, 10 times 10 to the minus 9 coulombs spread over this entire rod, and compare that with a point charge that has the same charge, 10 times 10 to the minus 9 coulombs, and this distance r is the same, I don't know, maybe 10 centimeters or something like that. Would we get the same electric field for the case of the point charge as the case of the rod? No, why not? The charge is spread out, right? Because the charge is spread out. So we saw last time how the electric field due to these pieces farther away are making, field contributions that point kind of like that, right? So these delta E's kind of point like that. And so you're going to get some cancellation here. And so what would you expect? Would this electric field be bigger or smaller? It should be bigger for the point charge case than for the rod case, right? So one thing we could do is actually plug in and see, do we get a number that's smaller than what we would expect for a point charge? That might be a good way to test it. But we need to know what to expect there, right? We're not going to get the same electric field. We're going to get something that should be smaller. When would this behave like a point charge? Let's think of it this way. When would this kind of situation look like a point charge? What would have to be true for it to be similar to a point charge situation? Yes. The length near zero, right? So two things. Either if you have a rod that has a length that's very, very small compared to the distance away, okay, or if you just get farther and farther away, right, so that it looks more and more like a point charge as you get farther and farther away. So in other words, we're looking at a case where the length is much smaller than r, okay? Well, let's look at the denominator here. If you have r squared plus L over 2 squared, if L is a lot smaller than r, then when I add these two things together, that's going to be approximately equal to just what? R squared, right? Okay. Put that back in. We have then the electric field of the rod being equal to 1 over 4 pi epsilon 0 Q over r times the square root of r squared, and the square root of r squared is r, and so we get in the denominator r squared. Is that what we expect? So, yeah, because now it's looking like a point charge, right? So in the case where L is much less than r, it's giving something that's reasonable. So it looks like this is a good check, right? This is working out. There's another special case that we should think about, which is what happens when we have the opposite situation. What happens when we have a case where we're very close, our observation location is very close to the rod. In other words, R is, R is much less than L. R is much less than L. So imagine a case like this, right? So here's the length of the rod, and that little tiny distance is R, okay? Well, let's just plug it in and see what happens. In this case, if r squared plus L over 2 squared. If R is much less than L, then this should be approximately equal to just L over 2 squared. Okay. Plug that in, we have electric field of a rod magnitude is 1 over 4 pi epsilon 0 Q over R times the square root of L over 2 squared, which is just going to give us L over 2 in the denominator. And if I rewrite this a little bit, I can say 1 over 4 pi epsilon 0, invert the fraction here, and I have 2 times Q over L over R. So this is the magnitude of the electric field of the rod in cases where R is much less than L. And that's a very useful special case. Okay? If you have a very, very long, thin charged rod and your observation location is close to this charged rod, then it becomes a much simpler expression. And notice the distance dependence. First of all, in the numerator, we have constants, right? We have a charge per unit length. The length stays constant. We have the constant out front. And so all we have is just a 1 over R distance dependence, okay? Compare that to a 1 over R squared for the case of a point charge, or 1 over R cubed for the case of a dipole, right? So in this case, it's just 1 over R. The field's going down with distance, but it's not going down as rapidly. So if you double the distance away, the electric field is now 1. How much does the electric field decrease? If you double the distance in a 1 over R distance dependence, it's halved, right? It's halved, right? As opposed to if you double the distance away from a point charge, the field goes down by a factor of 4, right? So it doesn't it decreases much less rapidly than a point charge, okay? So you say, okay, that's great, but so what? Because that formula we worked out only for one particular situation, right on this perpendicular bisector, and how often is that going to be true? Well, if we take a look at a little program here, the usefulness is that if you make some approximations, we can get away with using this formula in situations where we're near that axis, maybe not directly on it. So for example, if I have a charged rod here, so this red cylinder is a uniformly charged rod, and I'm not sure if you can see it on this picture, but there's a little green line running parallel to it, which is just a line of observation locations near the rod, okay? So it's very close to the rod compared to its length. So if we, and this is a positively charged rod, so if I calculate the electric field at this location, it points directly away, as we would expect it, okay? If I move to a location that's not on that axis, but just somewhat farther away, well, that electric field looks pretty close to the one right on the axis, right? It looks like it's approximately in the same direction, has approximately the same magnitude as well. And I can do that here, or here, or here, or here. And you see, even as we get, quarter of the length away from the center, it's not looking too bad of an approximation to say that magnitude is just 1 over 4 pi epsilon 0, 2q over L over R. Just use that because it's pretty much the same length vector for all those cases. And even the direction is approximately the same. It's starting to get a little bit off of radially away as we move farther and farther toward the end. And if we get way down here, it's not a very good approximation at all. It starts to look very different. But when we're close enough to the center, and even if we're not all that close to the center, but if we're close enough radially away, if the R is much smaller than L, then we can get away with using that approximation in places where at first glance it might not seem to apply, right? We can say it's approximately pointing directly away from the rod and approximately has this magnitude, even in locations kind of off axis here. Okay, so approximations become very important. We can try to make our lives a little bit easier by looking at a physical situation, looking at the charge distribution, looking at the observation, where the observation location is, and seeing if we can make a decent enough approximation. And then if you can't, you need to go to other methods. Maybe you have to do it numerically. But at least as a first pass, it's always it can be a good guess. Okay. Everybody okay here? Another program just to show this a little bit more clearly in 3 dimensions. Open this up. Remember last time we had worked this out for the case where we were on the y-axis, and so we had a y down here, but then I just flipped it to L, or excuse me, I changed that y into an R. Why are we doing that? Well, there's a radial symmetry here, right? I mean, it doesn't matter if we're on the y-axis or if we're on a z-axis. From the point of view of the rod, it looks exactly the same. You're some perpendicular distance away from the center. And so if we were to look sort of down the axis here, you can see, again, these are a series of positive charges. We see that it tends to point away from that positive charge. It looks the same no matter how we spin it. Okay, so there's sort of a radial symmetry here, at least especially when we're close to the axis here. And at this center, all these electric field arrows along a circle the same distance away from that center surrounding that charge rod are going to be the same magnitude pointing radially away. Okay, so it's just giving you that sense of the symmetry of the situation here. Okay. Questions? Let's try a quick calculation. So we have a thin rod, 2 meters long, with a charge of negative 2 times 10 to the minus 7 coulombs, lies on the x-axis centered at the origin. What's the direction? What's the electric field? What is the electric field as a vector due to the rod at location 0.03, 0.050 meters? Okay. So talk to your neighbor, draw a picture, think about approximations. Are we able to get away with using the approximations that we talked about in this case or not? And think about the direction of the field. Okay, so we have a number of different answers. We have 3 is popular, 0, negative 3.6 times 10 to the 4th, 0 newtons per coulomb. 2 is popular, and 5 is popular. Well, okay, let's take a look at this. First of all, we have a rod that's 2 meters long, and the observation location is 0.03, 0.050 meters. So that's 3 centimeters, comma, 5 centimeters, comma, 0, compared to, this is 1 meter, and this is 1 meter. So 3 centimeters over and maybe 5 centimeters up, I don't know, is maybe right there. Okay. Can we make the approximation in this case to just treat it like a thin rod where we're very close to the, our observation location is very close to the charge, and we're not too far off the axis, right? So this seems like a good place to make this approximation, right? So already we know that the electric field is approximately pointing in what direction? It's a negative charge. Should be pointing down, right? It should be there's going to be a slight lateral component, right? But essentially, since I'm so close here, my vector is going to go through the rod, but that's okay. I'm drawing a different color. The electric field is pointing downward. Okay, so we should get a net electric field like that. So let's try it. We have the electric field of the rod. Remember, this is just a magnitude, so the vector, you often have to sort of construct the vector yourself based on the sign of the charge. So we'll just get the magnitude. The magnitude is going to be 1 over 4 pi epsilon 0 q, 2q over L, and it's really the magnitude of q, over r. So we have 9 times 10 to the minus, 9 times 10 to the ninth times 2 times a charge of 2 times 10 to the minus 7. And yeah, I know it's negative, but we're just looking for the magnitude. Divided by L. Okay, so the length is 2 meters. And what's R? Right, so that is what number? Is it 0.03 or 0.05? 0.05. Okay? So what do you get when you plug that in? I didn't even actually work it out. It's going to be, well, the 2's are going to cancel. You get 18 times 10 to the second divided by 0.05. So what is that? Okay, so it's 3.6 times 10 to the fourth. It's just a magnitude. It's just a magnitude. Okay, so I'm writing Q here, but the way to think about this, it's really the absolute value of Q because we just found the magnitude of these electric fields. Okay, so magnitude is always a positive number. When you want a vector, though, you have to look at the physical situation. You say, okay, this is a negative charge. I'm above the negative charge. It's got to be pointing towards it. So when I would write the vector, the electric field of the rod would be 0, negative 3.6 times 10 to the fourth, 0 in units of newtons per coulomb. Okay? Everybody okay? Questions?